need to include in your introduction for the second part. Remember, it is a two-part experiment, but you're writing one report. So your report needs to be a cohesive story beginning to end. It's not, this is what we did in part one, this is what we did in part two. Try and incorporate it all as one big thing. All right? So what extra things would we add for our introduction? What did we try and do? Or what are we trying to do? Part two. What we're concerned about is seeing how temperature affects our rate constant. So we kind of have the idea that temperature is proportional to our rate, but we don't have an exact relationship. So what we're really trying to do is flesh out that relationship, see exactly what's going on with it. Thankfully, we aren't trying to prove it all the way from back to basic principles. What we're going to start with is the basic principles and ultimately prove those basic principles. Okay? So what are the basic principles that show the relationship between temperature and rate? Okay? What we're looking at is the Arrhenius expression. So we know that our rate constant is equal to our orientation factor, frequency factor, times e to the negative activation energy divided by r times temperature. Okay? So what we want to do is come up with an experiment that allows us to see that. Okay? So as far as our experiment goes, we can monitor temperature and we could monitor the rate. Our expression doesn't directly show rate, but it does have an appearance in our Arrhenius expression. Where does it show up? K. We know our rate law is rate equals K times our reactance, our reactance to their respective powers, right? Okay, so we know that our rate is directly proportional to our rate constant. So we can generate some data here. Okay, so we can see how temperature directly impacts our rate by seeing how it affects our rate constant. Okay? So now we'd go back and say, okay, what can we do? Can we monitor the temperature? Yeah. Can we determine the rate constant? Kind of, sort of. How would you determine the rate constant? Equilibrium constant is products over reactants, so we can't do that. The concentration, or our rate divided by our concentrations. But to do that, what do we need to know? We need to know the orders of our reaction. Okay, so one of our limitations with this experiment is that we need to know our rate constant. And to solve for the rate constant, we need to know the rate law. So if we look at just part two on its own, we've got a problem because we don't know the rate law. So how do we figure out the rate law? What's that?
Part one's data?
Yeah, we go back to part one. So the reason we did part one was ultimately to get us the rate law so that we could actually determine this extra information. Right, that was the whole, or one of our big goals of part one. So once we've got that rate law, we can now go back and determine our rate constants as our temperature changes. So that's kind of nice. Okay? So what other things would be problematic within this? Okay, so we can for sure get our rate constant. We can also get our temperature. Is there going to be a problem or a complication with our temperature? Yeah, we're going to get fluctuations in our temperature. We have to make sure it stays constant. What if the temperature changes? The rate constant changes. Okay, so what we want is our temperature to stay as constant as possible. That's a bit difficult to do in most environments. In our undergraduate lab, it's near impossible to do. We're going to be using the hot plates, which are on this wall, if you don't remember that, to try and heat up some water baths. Those water baths will then be where we'll put our reaction flasks into them. Okay. Problem with trying to heat using those water baths is they're notoriously inconsistent. Okay. Okay? If you look at the dial, it doesn't say 40 degrees or 30 degrees. It says 1, 2, 3, 4. What do the numbers mean? Most cases, a fat lot of nothing. Okay? In general, what they're supposed to mean is 4 means it's on for a really long time. It just stays on. 1 means it cycles. Stays on for a little bit and turns itself off. Okay, so as we crank the dial from 1 to 4, its off cycle is less frequent. Does it kind of make sense? So what we would need to do is control that dial so that we maintain roughly 40 degrees in our water bath. Why use the water bath at all? Why not just heat directly on the hot plate? What happens when the temperature turns off or when our hot plate turns off? Temperature drops. If we've got a water bath that's heating, that temperature fluctuation should be relatively minimal. The water will help hold the heat for long enough until it starts to heat back up that we should see a relatively stable temperature. Okay, so our water bath is helpful in that respect. Okay, so getting our temperature to stabilize, why we use our water bath. Next big issue with the temperature. Okay, this may kind of depend on your experience so far with our hot plates. How consistent are our hot plates?
Very.
Super accurate, right? You turn it on at 1, that definitely means it only heats a little bit. No. Okay. A lot of our hot plates have electronic issues within them. So some of them, when you turn them on, it's not it's on only for a little bit. It immediately jumps to it's on the whole time, which means you're putting in tons of heat. So your temperature is going to continue to increase. How do you know what the hot plate's going to do? You get to do it. You get to monitor it and see what happens. Okay? In general, assuming the settings kind of hold true from yesterday's lab, it looks like a setting about 2, 2.5 will get you pretty close to 40 and stable at 40. Okay? I didn't watch too carefully to see what happened for the 30-degree mark. But 40 degrees looked like a setting about 2, 2.5. Okay, so that should help you guys out. It takes time to heat up water, so when you get into lab, that's probably the first thing you should do. Get your water bath going, get those solutions hot, okay? So that hopefully by the time you've got your solution A and B ready for the experiment or ready to be heated, your hot water bath is already ready to go. You can put it in, get it equilibrated, do the reaction. So there's less delay factor, okay? We do have some temperature inconsistencies there. So what happens if our temperature changes? Your experiment is ultimately going to fail, but we want to come up with some way that we can kind of average that out. We're going to hope it doesn't change by much. So what we can do is monitor the temperature during that course of the reaction and record the average temperature, whatever that may be. Okay? And that will be the temperature you'll use for all of your calculations. To determine the rate law, we need our orders. We're going to be doing the exact same experiments that we did before. So you're going to be going back to that same room, pipetting out the same solutions. You're just following that table. Now all you got to do is record the temperatures at which your reactions occurred as well. Okay? So nothing new as far as the experimental setup goes. When we go through and obtain this, so let's say we get our rate constant, we get our temperature. What information does that give us? We could then try and plot it, but we'd have to plot it to match this equation. That equation is an exponential equation, not the easiest to see or to get Excel to fit properly. So what we want to do is to be able to tweak that data into a more interpretable form. What's that more interpretable form? What's that? Yeah, we'll go through and take the natural log on both sides, and we'll get the natural log of K, our rate constant, will equal negative the activation energy over R times 1 over T plus the natural log of A. So once we've got our data collected, we can then go into Excel and start to manipulate it. All right? When we go through and do that, you'll have to plot 1 over T as what? As the X value the natural log of k will be the y value. So now when we go through and plot this, what do we start to find? We should hopefully see a straight line. What information can we pull off of that straight line? We can get our activation energy because the slope of that line is equal to the negative activation energy over R. Right, we can now solve for the activation energy. We can also solve for the frequency factor. What is the frequency factor related to? The y-intercept. Our frequency factor will equal e to the b. So the end result that we would end up summarizing from our overall experiment from part 2 would be the activation energy and our frequency factor. Those are our two big results. So easy, right? We just monitor temperature and we determine the rate constant. How do we determine the rate constant? Rate over these concentrations. Do we know those concentrations?
Yes.
Kind of, sort of. We have to go through and calculate them just like we did with part A. So what you're going to end up doing is part A calculations beginning to end with a bunch of extra stuff. Okay? So it's a lot of calculations to go through. Again, you can do it by hand or you can use Excel. The Excel file is posted. As far as what your in-lab would look like, it should be very similar, except now we have a temperature column, and everything else is pretty much the same. All of our solutions are in that back room. You can go and get them from there. You've got the hot plates closest here. Difficult to maintain the temperature, so be aware of that. I would recommend that you start your water bath getting to 40 degrees when you start the solution. We are going to talk through a bunch of calculations first, just so you know. And then hopefully for your first solution, we'll get to 40 degrees. You can run your 40-degree tests. While you're waiting for the 40 degree, you can do the 0 degree Celsius one. Once you're done with the 40 degree, you can drop it to 30 degrees and you should be done. Okay? Done. Most students finish 30 to 40 minutes early. Okay, just to give you a heads up on time. Okay, so let's go through the calculations once more, kind of get a feel for what's happening there. We do have the Excel file. This one's part A, so what we can do is look at part B. Our part B calculations. I went through and added an extra worksheet. So if you go down to the bottom right-hand corner, or that's my left-hand corner, there's another worksheet tab. So you can open up that tab and go to where you would enter in your part B calculations. I did not directly copy and paste the form or the cells over appropriately. So if you copy and paste your formulas, your cell references are probably going to be wrong. Okay, so be aware of that. Yes?
Can you make it a little bit bigger because it was hard to see in the video?
Let's see if I can sneak it even bigger than that. How's that? Hopefully that'll work a little bit better. I didn't get motion sick. Sorry. That was mean. So we'll go through and enter in all of the data again. Did I copy and paste it? Yes, I did. So what I've copied and pasted over are just the experimental results or the experimental concentrations and time from part A. Your volumes. Those volumes will change. They aren't exactly the same. So make sure you enter in the correct volumes. You'll notice that there are some new cells. We do have a temperature cell showing up in here. This shifts the cell values. So if you just copy and paste your formulas across from the first Excel file, it's not going to copy and paste appropriately, and it's going to start referencing weird cells. Okay? So it's probably best to go through and just re-enter in the formulas to make sure you're referencing the proper places. Okay? Because you're going to have to do it anyway, so I would just ignore the copy-paste issue. Okay? When it comes to temperature, You will be recording it in degrees Celsius. Let's go ahead and say this was your 40 degrees. When we go back to the Arrhenius expression, do we want degrees Celsius? No, it needs to be in Kelvin. How do we convert Kelvin? Plus 273, so we can hit equals to tell Excel to do the calculation, plus 273, return, and we clicked on our cell reference, and now we can lower right hand corner, click and drag, and it should copy that calculation. Okay, if we go through just for the sake of it, say what the other ones are. Oops. Click and drag down, it did all the appropriate calculations, right? Again, we're going to go through with just the first 2 times because that's all I got. Okay, we can go through and determine the, let's do iodide concentration. How did we determine the iodide concentration? What did that equal? Iodide. That was what? So we do have a concentration value. Okay, let me open up this cell a little bit so we can see it. We do have a concentration of Ki in the burette. Is that the same as the concentration in your reaction? No, why not? We dilute it with a whole bunch of other stuff. So the volume changes, so we can't say it's directly the same, but it is related to it. How is it related to it? The volume that you added. Okay? So we can say the volume of our Ki that we added, we can multiply by the concentration, and you can do the hold cell reference if you want, or we can just put in its concentration, 0.3. Now we don't have to worry about that referencing issue. Okay? We now want to divide by the total volume, which thankfully I calculated. So we can see an extra thing here. We would want to go to our total volume column and click that column and hit return. We're going to get that div 0 error because we didn't calculate the total volume. How do we determine that? Add everything up. I'm going to do sum, click and drag. Gives me the 40. As soon as I enter that number, it does auto-calculate because that cell reference has changed. Okay, so that's kind of nice. I'm going to click and drag on that, and I'll click and drag to propagate this one as well. How do we calculate the peroxide concentration? Same idea. We'll take the volume times the concentration of the peroxide, which was 0.1, divided by the total volume, and we've got our peroxide concentration. Click and drag again. How do we determine the rate? What concentration over time? Iodine. So we'll go back to our iodine. Whoops, I don't have a value there. Doesn't matter, we already started with it, so let's go ahead and enter it. Our iodine concentration divided by time. We're going to get 0. Why would we get 0? There's nothing in the iodine column. So now we go back and figure out what our concentration of iodine was. How did we do that? It's related to our thiosulfate, so we can say it's equal to, where's thiosulfate? The volume added of thiosulfate times its molarity divided by the total volume. Whoops. Change the molarity. But that gives me the molarity of thiosulfate. If we divide by 2, that now converts to our iodine concentration. Okay, it still says 0, but that's because the cell wasn't big enough. Okay. Why divide by 2? How'd you get that number? The mole-to-mole ratio that came from the balanced reaction equation. Okay. We can again click and drag, and we now have our rates. Yes?
So you don't need any of those dollar signs anywhere?
I don't need the dollar signs here because instead of clicking the cell that had the concentration, I just entered the number value for the concentration. So I didn't have to worry about the dollar signs. So I kind of cheated in this case. Okay, our rate constant. How do we solve for the rate constant? that'll be our rate our rate divided by what? Our concentrations of Ki. I think I heard someone say it, to whatever order, so we'll have to include the caret for whatever our order was from part A. Anybody have an order number? So that's our order with respect to that one. Times, well, doesn't really matter.
Well, Ki is 0.88.
So for Ki, we put in our order as 0.88. For the peroxide, we'd put in our order as 5. We can end our parentheses and hit return. Click and drag and we'd get our rates. Okay, again, we got just a really small number. Our rate constants. Okay. Would we expect these rate constants to stay the same? Yes and no. For these two trials, we would expect them to stay the same because the temperature is the same. But if we compare to the other trials, no, because the temperature is different. Okay? So watch out for that. The one extra thing you're going to add here, you are going to include your rate constant from experiment A, okay, or your first part. So when you go to plot your data, you should have 7 data points. If you don't have 7, you will lose points. Okay? So you'll also need to include its temperature. We can go back to our 1 over T, because when we go to plot, we want to plot 1 over T, our temperature, versus the natural log of K. 1 divided by our temperature in degrees Kelvin. Return. Man, this whole, not being able to see, it's irritating. Our natural log of K, to do that, equals ln. You need the parentheses. Reference our cell. Okay. We now have everything that we want to plot, so we can go to the graph. Okay, so we can click on that box. It's got the correct graph setup chosen. If you don't want to use it, that's fine. You don't have to use it. Select data. We'll add a new series. The x values need to be 1 over T. We can click and drag for our 7 data points. I think that's 7. And we'll click the same range for our natural log of K. And now when we look at our graph, we should see our data points. Okay? Pretty useless graph right now because we only have 2 data points. Okay? As far as what your graph should look like, at least as an approximative effect, you should see probably these last 2 for some reason seem to be spaced a little bit. You'll see them kind of on top of each other. But in the rest of them, you'll probably see data points somewhere along a little bit closer to each other, and then the last set is almost directly on top of each other, and you'll see one more somewhere in there. Something along those lines. Okay? What do we want to do now? We want to add the trend line. With all of the data there, adding the trend line will make a little bit more sense. With only these 2 data points, the trend line is going to be pretty useless. And in fact, yesterday it gave me error messages. Whoops. We would click on the data, so the data should highlight. Right click, add trend line, and it gave me the same error message. It should pop up with a window telling you what your trend line options are. You want linear, display the equation. Okay? So that is then going to spit out and give you a straight line through your data. Should look something along these lines, and it will tell you y equals negative 6,023 x plus 17, or a box, whatever you decide that looks like. Okay? What do we do with that information? What's that? So frequency factor, which was A. What did we say A equals? E to the B, what's our B?
17.
17. Plug that into our calculator. We now know what our A value is. We can report that both in our calculation section and in the abstract. Okay. What's the other thing we can do? Solve for the activation energy, which was M, our slope, equals negative 6,023, which equals negative EA over R. Our activation energy ends up being our 6,023 times 8.3145. Why the 8.1 and not the 0.08? We need the correct units. We'll have to use the 8.31 because that's got the right units for us. Okay? If the last group did everything correctly, I believe your activation energy comes out to something like 55 kilojoules. Okay? If your slope is not negative, what does that mean? What would that do to your activation energy? That makes your activation energy negative. What does that mean? If we looked at an energy diagram, where this was our reactance and this is our product, where's our activation energy? At least for the forward, it's our reactant to transition state. Can that number possibly be negative? That means we've got this weird negative slope for an activation energy. That doesn't make physical sense. I can't even draw it. Okay? So what does that mean? Somehow or another in your calculations you mess something up. Go back through and carefully check. More than likely you made a sign mistake, something along those lines. Okay? So that should get you set up with all of the calculations. The very last thing that I want to talk about would be what to kind of put into your calculations section. So this report is the abstract, which we talked about on Monday on what things need to show up in that. All your important results. So your overall rate law, your rate constant with a standard deviation, okay? And then your activation energy and your A value, okay, your frequency factor. So those results all need to show up in your abstract. We don't need to see anything about volumes or anything like that because those were experimental results, not your final result. Okay, so we're concerned about your end goal. As far as what we would expect for your calculations section, so let's kind of approach this. Our results/calculations. You could go through and show me all the volumes of each of those individual samples, except did you actually use those volumes to determine your final answer? Kind of, sort of. You had to use them to get to a point, but really what you were using was generating your first table. So we would get table 1 for part A. So your table would have some fancy title on top of it describing what that table shows. We would have within that table experiment, well, let's call it trial. Trial, and then you've got 1 through 5 for part A. Then you have the concentration of iodide, concentration of peroxide, and your rate. You can add other things in there if you would like to, but that's what I would expect to see at this point. Okay, we will add an extra column in a second. Okay, at that point you've got all of your results there nicely summarized. What did you do with those results? Or how did you get those results first? First, we should show some calculations here, because you've got those concentrations, right? So how did you get the concentrations? What I'm going to expect you to show me is how you get the concentrations for iodine. So give me a generic solve for that. That says generic. Okay, units, values, your coefficients. Okay, I'm going to assume that if you can do your iodine calculation correctly, that you can do all the other ones correctly, because the iodine, I think, is more advanced than the iodide and the peroxide. Okay, so you'll give me that generic solve, and then you'll give me with numbers. So pick any trial you want and show me that calculation. Okay? After that, we do have a solve. Great. I don't remember what I said for Tuesday, Thursday. Show me how you would solve for the rate. It's a nice simple calculation. You don't have to plug numbers in. That would be your iodine over your time. Right? So now I know how you got all of the values in that table. Okay? What did you do with those values now? Part A. You all finished those calculations, right? So what'd you do?
We plotted it.
You plotted sections of your data. So you would then have two figures. Call this figure 1, figure 2. Those figures should now have some description telling me what those figures show. Okay. Underneath each of those figures, I would also expect some calculations. Those calculations are ultimately coming from rate equals k I minus to the x, H2O2 to the y. Whoops, sorry. This is going to get really crowded here. For figure 1, if it is indeed figure 1, it's going to depend on how you decide to order it. You went through and plotted the log of the rate versus x times log of I minus. Plus the log of a new rate constant. Why do I want to see that information? Because that explains how you got that graph. What information did you use after you got that? The graph gives you the slope. The slope is the order from your equation. You could then summarize that with x equals whatever that number is off your slope. So x equals your slope number. You repeat those calculations. Green was an awesome color for that. Repeat that sequence of calculations for figure 2 as well. Okay? So at the end of all of that, you would then be able to tell me that your rate equals K times the concentration of iodide to the 0.88 or whatever it actually is, peroxide to the 1.045. Breathe. Rate, we're just going to pretend the rest of that's still up there. Rate equals our rate constant. Iodide to the 0.088. H2O2 to our 1.045. What was the next step? The rate constant. So you would tell me K equals, solve for it generically, and then say K equals with some numbers. Okay? Awesome that I deleted that table. One extra column that I would add to table 1 then. So let's go back and say we had table 1. We had what? Trial, I minus, H2O2, rate. What's the one extra column? give me the rate constant. And list that rate constant for each of your trials. The very, very bottom of your table, you can give me an average rate constant. Why do I not want an average for anything else? Because nothing else is a constant. Okay? So it doesn't make sense to use those. This rate constant is what you will then translate into part B. Okay, so what do we expect to see for part B? So now I'm going to go through and erase everything intentionally this time. When we move to part B, we still needed that same type of table. So we'd start with our trials, our iodide concentration, the peroxide concentration, the rate, okay, and for that matter, the rate constant. Okay. You should be able to give me the rate constant. Oh, one more thing on that. Can't believe I forgot that. What's the other important thing that we need to add? The temperature. Okay. You don't need to show me any of those calculations. Why not for any of those values? What's that? They aren't plotted. You already showed me how to do all those calculations. That was part A. Okay? For every single one of those. So you don't need to show any calculations as far as that goes. What you would then shift to would be a new graph. So here we get figure 3, nice and sloppy, with again your explanation. In figure 3, what do we have? That's your slope with your line. That figure 3 is a plot of your Arrhenius expression. The ln of k equals negative EA over R, 1 over T, plus the natural log of A. You can then tell me that the slope equals negative activation energy over R, B equals ln of A. Solve for your activation energy, solve for A. And you can do that with numbers from there. Okay? So as far as what calculations you have to show for part B, it's very, very limited. There isn't a whole lot to really show. All you're doing is just plotting and interpreting directly off the plot. All of your calculations are really going to come in from part A. Okay? Questions about any of that? Okay, so if we don't have any questions, then we will go ahead and call this quits. I will go ahead and